So, okay, let's start. First thing, the link here is this is a link to a Dropbox folder where I put the outline, so you don't have to copy it, and the goals, and I will update the outline, and I will put some scan of the notes, but I probably will do it today or tomorrow or by the end of the week. Okay, so let's say by the end of the week all the material will be there. Here you have the outline. So yesterday we more or less arrived up to this point, so I'm going to continue today. And the goals. So and okay, this is a summary of the first of yesterday. I'm afraid you cannot read, but you should have most of it in your notes. But just to go quickly over it, so we are looking to the perceptron problem in a setting that is that of a random constraint satisfaction problem. So we have the problem is to find some vector x that belongs to the sphere of radius n in n dimension, radius square root of n in n dimensions, such that these constraints are all satisfied. So I have m constraints, and each constraint is that the projection of x on a given vector should be bigger than sigma, and the vector phi is each component of the vector phi is a random variable with Gaussian with zero mean and variance 1 over n taken independently. And I'm going to take the thermodynamic limit with n and m going to infinity. We fix the ratio alpha m over n, so the control parameter of the model are alpha and sigma. Okay. So the second thing I did is to encode this into an Hamiltonian. So my Hamiltonian is the sum over all the constraints of some potential v that is positive if the constraint is not satisfied. So if the argument is negative, and is 0 if the constraint is satisfied, so if the argument is positive. The potential is something like that, so it's 0 and then something positive. You can, for the moment it's arbitrary. And okay, so in such a way that the Hamiltonian is 0 if all the constraints are satisfied, and it is positive if at least one constraint is not satisfied. And then I said, okay, then we can introduce the partition function, which will be the integral over x. This calligraphic d is the integral over the sphere, so it takes into account the spherical constraint of the exponential of minus beta h. And I said, okay, if I have solutions to the constraints, so if I have states with zero energy, in the zero temperature limit, this thing is going to be the volume of the space of the solutions. And if not, in the zero temperature limit, this will go to the ground state, which will be the minimal energy, which will tell you the minimal amount of unsatisfied constraints, if you want. Now, this was the second step. The first step was to say, okay, we cannot compute z exactly. I mean, unless, okay, on a given finite side system, we can do it by message passing, but this is not the aim of my lecture. So I want to take the thermodynamic limit, and I want to have an analytical expression as simple as possible. So what I do is I take the log. I use the fact that the log is self-averaging, so I take the average of the log, which is easier to compute. And then we did the replica calculation, so to average out, we wrote log z as the limit, blah, 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 of z to the n, and so on. We took the average over the disorder, and then we end up by saying that the free energy is given by minus t times the limit for n going to 0 of the maximum over a matrix Q A B of some function a of this matrix. The matrix Q has to be symmetric, and it has 1 on the diagonal. The 1 comes from the spherical constraint. And the expression of A is very simple. It's just 1/2 log that Q plus alpha, which is the ratio of constraints to variable, times logarithm of a function I of Q, which I wrote here in a very compact form. Is just the integral over small n variables that I call R, that are Gaussian variables with zero mean and covariance Q, sorry, Q minus 1, of the product of the exponential of minus beta V. Okay? Anyway, we are not going to use this, so it's just for completeness. This computation, by the way, is very similar to the one you would do for the p-spin model, for the spherical p-spin model. So the log that Q is standard, is there for all the spherical models, and the only thing that will change is this function that is much easier in the p-spin than it is here. It's just Q to the p, basically, in the p-spin. Okay. Okay, and then we said, okay, now we don't know. In principle, we should find for each n the maximum of this function, and then do the analytical continuation to real n and send n to 0. This is difficult. So we will try first the simplest option, which is to assume that the symmetry that we have in this function a is satisfied at the maximum. So that this function is symmetric under permutations of the labels of the replicas. So if I say replica 1, I call it replica 6, and the replica 6, I call it replica 8, and I make a permutation. This function is the same. So I can say, okay, if I'm lucky, then the maximum will also be symmetric, which is not the case. There is no guarantee that it will be the case, because the maximum of a function that has a symmetry does not need to share the symmetry of the function. Okay, typical example is the Ising model. So, but let's try. So, okay, then we said, okay, let's try a replica symmetric solution. So if I want to keep the symmetry between the replicas, then my QAB can only be equal to a unique value Q for all A different from B. And it is always 1 on the diagonal. And this is just because if I change the labels, Q must be the same. So I plug this into this function. We computed it, and we took the limit n to 0 before doing the maximization over Q. And so in the end, we get that the free energy is minus T times the minimum over Q of some function A of Q. Here, the minimum, I told you, comes from the fact that when you do the limit n to 0, you have a 1 minus n in front that will change the sign and then the concavity of the function. And if you want to check this, I suggested as an exercise, just put alpha equal to 0, just look to the log.q, try to find the maximum, and you will see that it will change sign when n goes to 0. And the function a of q is going to be this, 1/2 log 1 minus q plus 1/2 q over 1 minus q plus this double convolution with a log in between. Okay? Okay, this was the long calculation part. Now calculations will stop and will just mostly be hand waving, but okay, with a little bit of calculation. So what I also did last time was to say, okay, let's now look to what happens in the, now I want to, from this I want to study the SAT-Unsub transition. So the first thing I did was to look to the SAT phase. And I said, okay, in the SAT phase, what we expect is that t goes to 0 with q finite. And in such a way that if q is finite, then the function a of q will also be finite. So the free energy will be just minus t times a of q star. And from this is a constant, it is independent of temperature. Let's call q star the minimum. And then what I get from this is that the entropy is just a of q star, and the energy is 0. Okay, because the free energy is E minus Ts. If it's linear in T, if it's proportional to T, then I get this. Okay. So this means that I am in the SAT phase because I have 0 energy, so the constraints are satisfied, and I have a finite entropy, so I have a finite volume of solutions to my problem. And okay, what I said also is that, okay, now if you want to take this limit, so t going to 0 and q finite, the only thing you have to do is to put beta equal infinity here, which will simplify a little bit the expression of a. And here you just, instead of e to the minus beta v, you will get a heaviside function, and this convolution will give you an error function. And then, okay, and from this domain you can do it numerically, it's very easy. You can do the optimization over q, and you can compute the entropy. And then the next question is, okay, now let's look to the SAT-Unsub transition. So let's try to say, okay, at the SAT-Unsub transition, and this I forgot to specify, this is true for a model with continuous variables, which is the case here, but it will not be necessarily true with discrete variables. But if you have continuous variables, when you approach the SAT-Unsub transition, the space of solutions will go just to a point, okay? And then this means that q must go to 1. Why? Because q is the overlap between replicas, and if the space of solutions goes to a point, this means that all the replicas have to go to that point, because this is the only possible point you have. And then they all coincide, and then the overlap is 1. So then I said, okay, I wrote the equation for q, by taking the derivative of this, and I ask, when is q equal to 1 a solution to this equation? And this gives me a condition that is that alpha must be equal to 1 over the integral between minus infinity and sigma of a Gaussian times h minus sigma square. Okay, so this defines the Sat-Unsat transition. And if you plot it as a function of sigma, you get, okay, sigma for the moment is positive, you get something like this. So above is unsat and below is going to be sat. Okay? So gamma is just gamma q of h is just a Gaussian with 0 mean and variance q. So gamma 1 is just e to the minus h square over 2 divided by square root of 2 pi. Okay, so this is where we stopped yesterday. Now, what I want to discuss now is the unsat phase. Okay, so what I can do is to, let's look, for example, to a cut of the phase. So let's fix sigma to some value, whatever, and then we can look as a function of alpha, which is what we usually do in this kind of problems. Okay, so we fix sigma and then we increase the number of constraints. So we move from the sat to the unsat phase. So can you, okay, this one cannot be moved. Okay, let's do it in another place. Let's move here. So here I'm plotting as a function of alpha the value of q. So at alpha equal to 0, you have q equal to 0, then it's going to increase. And then I told you at the Sat-Unsat transition, it will reach 1. So above that point, it's going to stay 1. It cannot be bigger than 1 because it's the overlap between two replicas, and by the triangular inequality, it cannot be bigger than 1. Now, this is at 0 temperature, okay? This is t equal to 0. What happens if I put a finite temperature now to my problem? What happens is that, okay, at finite temperature, everything is analytic. Here, I don't have any singularity. This is a smooth thing. Everything is smooth. And what I expect is just q is going to do something like this. It's going to go smoothly from 0 to 1, which means that of course, at finite temperature, I have no Sat-Unsat transition because I can violate the constraints with some finite probability. So I will just increase the energy when I increase alpha, but in a smooth way. And then if I send back t to 0, then I have to approach this curve, so I'm going to get something like this. Okay? So which means that if I am in the unsat phase, and I look to q, now q has to go to 1 when t goes to 0. Right? So this means that in the unsat phase, the correct limit is to take t to 0 with q equal to 1 minus, and now I will write it in this way, 1 minus chi t, where chi is some number, and y is proportional to t and not to t square or t cube or square root of t, whatever. This is very easy, and you can try to do it as an exercise. You assume that you have just a minimum, and you have harmonic vibrations around this minimum. So each replica is, you assume that you have like two replicas, they are vibrating independently around the same minimum. Compute the overlap, which is x1 dot x2 divided by n. You will see that it is linear. So this is I'm assuming it's harmonic. I will check it now, but okay. So if I want to describe the unsat phase, which is now my free B, this is the correct limit I should take. So if I go back to the expression of A and I look to what happens when I do this limit, I see that, okay, first of all, okay, A is going to be divergent because there is a 1 minus q here, but what I'm really interested in is minus t times A, so that's fine. And the other thing that I see is that here I have beta going to infinity, and I also have 1 minus q going to 0. So the Gaussian is becoming a delta. So I have to work a little bit on this integral. It's easy. I will not do it in detail, but what you are going to find, now I will just give you the result, is that if I take this limit and I take the free energy, which is minus t times a of q, and I take this limit, so t going to 0 with q equal to 1 minus chi t, what do I get? So you see the log here is going to 0, because this is going to be log t times t log t goes to 0. The second term is going to be finite, because I have 1 minus q, which is chi t in the denominator, so it's going to be just minus 1 over 2 chi. Okay? This is the term q over 1 minus q. And this last term, I have to work out the asymptotic behavior of this integral. And what I get is alpha over 2 times the integral between minus infinity and sigma. I'm sorry. Okay, at this point I have to make a choice, because the asymptotic behavior of this now depends on the potential. So I cannot, for the SAT phase, I said, okay, the potential is not important as long as it is positive for H negative. But now I have to choose the potential. So just let's make a choice. We will take a standard choice in the physics of jamming, which is convenient, and it's just an harmonic potential. So I will say that if H is negative, my potential is H squared over 2, so it's a parabola, like I drew it up there. And if H is positive, it's 0. So it's really like when you have soft spheres, harmonic soft spheres. If you have an overlap, then you have a Gaussian potential, which means a linear force in repulsion. So if you take this potential, yes?
Does the result depend only on the first order plus weight equal to 0?
No, close enough to jamming, yes, but not in general. In general, it will be a function of the full potential, but of course, yes. Then when I will do the jamming limit, I mean the SAT unsat from the unsat phase, this depends only on the expansion of H around H equal to 0.
Does a linear potential provide
Depends what you call physics, but for example, yes, I will. So I was saying, okay, you do this asymptotic for this potential, and then what you get is H minus sigma square divided by 1 plus chi, okay? Which means that I can write this as minus 1 over 2 chi plus alpha over. So remember that this integral is the inverse of the alpha s. So this will be alpha over alpha s of sigma times 1 over 1 plus chi. Okay? So this is the free energy minus this is the free energy in the 0 temperature limit in the unsat phase. Sorry, yes. Of course, yes. It's gamma 1 of H. So, I mean, it's the same as here, sorry. I could have written it directly in this form. So, now this is a function of chi, which is still unknown, and since I have to minimize over q, what I have to do is I have to minimize over chi, because q and chi is the same, okay? So I have to minimize over chi, which gives me, and this is very easy to solve, it just gives you that 1 plus 1 over chi is equal to square root of alpha over alpha s of sigma. So let's put a minus 1 here. Okay, so you get, can you read here? Okay, so I got this equation for chi. And when I plug this into the free energy, I get, not before I write the result, note that now the free energy in this case has a finite limit independent of temperature, when temperature goes to 0. What does it mean? This means that the energy is the limit of the free energy when t goes to 0, it's the energy now, okay? Because as before, energy is equal, the free energy is equal to E minus Ts. So when t goes to 0, if this is finite, it means that the Ts term has gone to 0, unless you think that the entropy is diverging like 1 over t, which is not the case. And then the energy is going to be the limit of the free energy when t goes to 0. Yes?
Something happened to the locals for 1 minus q.
It went to 0 because 1 minus q is proportional to t. It's exactly what, if you want the entropy, this log minus q is the dominant term of the entropy. You can check it. And it's going to be log t. So the entropy is going to minus infinity as log t. But when you multiply by t in the free energy, you get t log t that goes to 0. So in the unsat phase, what is happening is that the energy is going to a finite value. The entropy is log t, and t log t goes to 0, so it doesn't contribute to the free energy. Okay, so the minimum of this thing over chi is going to be the energy. Okay, let's write it. Okay, I will write it down here, but I can read it, so you just to have a free blackboard for the rest. So the energy is just going to be 1/2, and then you have square root of alpha over alpha s of sigma minus 1 square. So, okay, so I can compute in this case the energy is a very, very simple expression of alpha. It's just this. And what happens now? So this was in the unsat phase. What happens when I go back? Now I'm at 0 temperature in the unsat phase, and I decrease alpha to go back to the transition. You see what happens? That at the transition, alpha is equal to alpha s. So the square root is equal to 1. So I get 1 over chi equal to 0. So it means that chi goes to infinity. Okay? So when I approach the unsat transition from the unsat phase at 0 temperature, so what happens is that chi is going to diverge, and the energy, which is this expression, is going to go to 0 like delta alpha square, proportionally to delta alpha square, where delta alpha, okay, alpha minus alpha s of sigma square. Okay? So this depends on the potential, Federico. So if you choose another potential, it will not be square. It will have the same exponent as the potential, basically, which is what you also see in when you ungem soft spheres. You see that the energy will go to 0 with the same exponent as the potential. But okay, I will focus on the harmonic case. Okay, so is this fine? So. And you see that the fact that chi diverges is good because, of course, I mean, chi is the speed of convergence of q to 1. So if I am somewhere in the unsat phase, q will go to 1 with temperature. If I approach the sat phase, q will go slower and slower because then below it should stay finite. So the fact that chi is diverging is the thing that you need to match with the other behavior in the sat phase. So this is the sat, and this is the unsat. Okay. So now just to last thing, the landscape. So what does all this mean in terms of energy landscape? If you believe that the replica symmetric solution is correct, and it is correct in this case, so for sigma positive, the calculation we are doing is exact, and I will explain why in a second. Then what is the picture that you get for the landscape? Basically, what you get is that in the unsat phase, your energy landscape. So this is the Hamiltonian as a function of x. Can you guess how it is? Okay, it's replica symmetric, which means that you have just one minimum. The minimum is isolated because you know that Q is equal to 1. So at 0 temperature, all the replicas go to the same state, which is the minimum of the energy. And it has some finite energy, which is exactly the expression I gave here. Okay? And you can check it. So if you want, this is really easy. You can write a code. You take the Hamiltonian of the perceptron. You take a system of 100 spins with some value of alpha. And then you just do gradient descent. So you do this. Start from a random configuration. Only subject is that you have to do gradient descent on the sphere, okay? Because the vector x is on the sphere. So you have to add the Lagrange multiplier to constrain the system to stay on the sphere. And what you will see is that you converge. You take any initial condition, you always converge to the same minimum. And the energy of the minimum is exactly given by this expression. Okay, 1/2 square root of alpha minus 1 square. Okay, so this is a check you can do. It's 10 lines of code. Now, what is going to happen in this is the unsat phase. What happens in the sat phase? And okay, by the way, you see, the system is going to be harmonic in the this is the unsat phase. The system is going to be harmonic because your minimum is a good minimum. So the entropy of harmonic system is log T. And the energy is finite plus a small correction. And you can also check that the overlap is 1 minus chi T. Yes, I think so. The only thing that depends, yes, because when you are in the unsat phase, what happens to the potential around the point doesn't matter because you are visiting states where you are. I mean, you are typically here. The only thing is that you need a smooth potential. If your potential is singular second derivative, okay, of course you are not harmonic. But what depends on the potential is how this thing goes to 0. And now what happens in the sat phase? Try a guess. Yes, so I should have a lot of zeros. So how do you expect this lot of zeros to be organized? So when I approach the sat phase, the sat and sat transition, this thing will go to 0. And then what is going to happen? It will be flat. So what I expect is something like this. So I will have a flat part, which corresponds to the space of the solutions. But it's a connected thing, because, and this is a consequence of the fact that the system is replica symmetric, or if you want, the fact that the system is replica symmetric is a consequence of that. I mean, the two things go together. It means that the replicas are all going to stay close together, and Q will be the typical size, will be a measure of the typical size of this space of solutions. So the entropy will be finite, and the energy will be 0, and Q will be finite. So when I approach the transition from the sat phase, Q will go to 1. If you want, 1 minus Q is the measure of the size of this thing. Q will go to 1, the entropy will go to minus infinity, and the energy will start to increase. Okay? So this is the simplest sat and sat phase transition that you can imagine, because your system is really going from one single minimum to one connected region of solutions with some energy, finite energy outside. Okay. Now, and you see that some of the properties that you see in jamming are already seen here. So the energy, for example, is quadratic in the distance from the transition, and so on. There is, however, a problem. So that's why I cannot stop here. That this system, when in this situation, what you find is that the jamming,
The energy being quadratic, is that a result of your potential being quadratic, or is that net wrong?
the energy being quadratic here as a function of x is general. The energy being quadratic as a function of the distance, so the fact that this value, that this thing is quadratic in the distance from the transition, this is specific to the harmonic potential. Now, yes?
Can you derive the result from the fact that the constraints that are complex?
Yes, yes. Of course, I'm going to that. So the last thing, okay, so now why I cannot stop here, why I want to do something more, is just that if you, and I will come back on this, so now I'll go quickly over this thing. So for those who don't know jamming, maybe don't be too worried if you don't follow. But the point is, I want to one important property of jamming is that the system is isostatic, which means that the number of constraints that are, if you want, the number of particles that are touching is equal to the number of degrees of freedom of the particles. So what does it mean here to be isostatic? What I should do, I should look to the number of things that are touching, which means if I call h mu the value of r minus sigma, so this must be positive or equal to 0. So the ones that are just touching are the ones that are equal to 0. Okay. So when I reach the Sat-on-Sat transition, it means that some of the constraints are starting to reach their saturation. So they're going to be 0. And I want to know how many of them are 0. And this can be computed analytically. It's very easy. So the fraction of, if I call connectivity, or I mean the fraction of things that are, of constraints that are exactly satisfied, is just this. Okay, this is a simple calculation that you find in the SciPost paper that I mentioned yesterday. So this is the theta function of sigma over square root of 2, where this is the heavy side smoothed by. So, okay, so, and if you want to be isostatic, then you wanted, okay, the total number of constraints that is, sorry. This is the fraction of constraints out of m. So you have m constraints, and how many of them are satisfied? This is, okay, the total number of constraints that are just touching is going to be z times m. Okay? I define z is the fraction of the constraints that are 0. So this means that being isostatic means this equality. So the number of degrees of freedom is n, because I have n particles. Okay, if you want n minus 1, because I am on the sphere, but okay. It's a 1 over n correction. So I have n degrees of freedom, and I have z times m constraints that are touching, which is equivalent to say that alpha times z should be equal to 1. And you can check if you plot as a function of sigma, you plot z times alpha on the jamming line. Okay, so you look on this line. Sorry, I'm calling it jamming line. Sat-on-Sat transition line. I will maybe switch between the two, but so if you plot this, what you find is that this is equal to 1 at sigma equal to 0, but then it's smaller than 1 for all the other sigma. Okay, so this means that your system, when you in this situation, the system is actually hypostatic in the language of jamming, which means it means that you have less constraints that are touching than you have degrees of freedom. So this is not satisfactory, and there are a lot of nice properties of jamming that will, I think, be introduced by Sid Nagel starting from tomorrow, that are a consequence of isostaticity, and so that you cannot reproduce in this situation. So that's why we need to do something, we need to work a little bit more. Okay? So this is, So what we have to do if we want to have a nice isostatic system at the transition in the perceptron is to generalize a little bit the problem. So this is for A. We are going to generalize the problem in a very simple way, which will be just take sigma negative. Okay? So until now, I was discussing the case of sigma positive. And now I'm going to, I mean, in the original problem, sigma was just the parameter that enters into the constraints, and there is no reason why I cannot choose it to be negative. If I do that, however, it's not, I mean, it's not anymore a class. I mean, if you think to the perceptron as a classifier, or, I mean, this is not very nice, sigma negative. But now I don't want to think anymore to the perceptron as a problem of machine learning or whatever. I just want to, I keep thinking to it as a constraint satisfaction problem, and then in that case there is no problem to choose sigma negative. So what happens if I choose sigma negative? So I think I will switch, let's do for B first. Let's look to the geometry of the problem first. So if I have sigma positive, then it means I have my sphere. This is the space of the variables, x. So I have my vector x somewhere. This is the sphere in n dimension with radius square root of n. And now I add one constraint. So if I add one constraint, what happens is that I'm going to fix a direction, random. This will be the constraint. And then I say, OK, the scalar product between x and phi should be bigger than something, which means that I'm going to exclude all the vectors that are here. And so the space of solutions with one constraint will be this one. So you see it's a convex space because it's the surface of the sphere, okay, around the vector phi. Now I put one more constraint. So this was phi 1, the first constraint. I put a second constraint that I call phi 2. This is going to be phi 2. And this will exclude, similarly, it will exclude some other region. So this will be excluded. So the space of solutions is going to be this one, okay? This part of the, but you see it's the intersection of two convex regions, because each constraint is selecting a spherical cap. I intersect two of them, it's still a convex thing. And if I keep adding constraints, the space of solutions will reduce, but it will be always convex, which is what I have here. Okay, so the image that we have here, and this is why the system for positive sigma is always replica symmetric, because the space of solutions is always convex, and okay, and that's it. Now what happens for sigma negative? Now let's see if I manage to make a good drawing. So I will put one first constraint. So now so this is going to be phi 1, the first constraint. This is the, now what I want is that the scalar product of x with phi is bigger than a negative constant. So it means, I mean, if sigma was 0, it would be equivalent to putting a plane like that. If it's negative, it's going to be something like that. OK, let's do, I will take sigma to simplify the drawing. So it will exclude this part. OK? What happens if I add one more constraint? For example, like this, is that I'm going to exclude this part. And now you see that the space of solutions is disconnected in two parts. There is this part here and this part here. Okay? So I have, already with two constraints, I can create two clusters of solutions, two groups of solutions that are disconnected. And if I want to go from here to here, I have to go through a region where the energy is positive. So if sigma is negative, I can hope to have replica symmetry breaking. And you ask, why do you hope so? Because I like it. No, because it will also give all the properties of jamming in this model. Okay, so we're going to study the negative case. Just a little thing that can be confusing, but I will tell it anyway, and if you're confused, don't worry. You can also interpret this as a kind of billiard, because you see that now each constraint, if you take the opposite vector, if you take minus phi, basically what's happening is that minus phi is excluding a region around it. So it's a kind of, if you think to the vector x, this is a kind of obstacle. So the negative case is like you are putting random obstacles on the sphere, and each obstacle is excluding something. So it's like a billiard. Okay, it's like a billiard on a sphere. So it looks more like a problem of particles, because you can think that you have a particle that is moving on the surface of a sphere, and there are these obstacles that are okay. Yes.
So is the idea that in a high-dimensional sphere, the probability that these small cones will intersect is diminishing is small, so
Say it again.
the probability that the cones will intersect is small, so that we have clusters of...
No, they can also intersect. I can add the third constraint, for example, like this. No, green is a bad color. Pink. No, pink is bad too. Yellow. Okay, yellow is also bad. Purple. Okay, I can add one more constraint that can intersect with this one.
So what
But still, it's not. I mean, if the constraints intersect, this is not a problem. What is important is that you are excluding regions. So if you exclude a sufficiently high number of regions, you can create these connections in your problem. Okay.
For creating this connection, shouldn't alpha be pretty close to 1? For creating those exclusions in those regions? That also depends how many
Of course,
constraints you
it depends on how many constraints I have, and it also depends on sigma. So I'm coming to that. Sure, you're right. So, okay, let's, okay, here, that's one. Now let's look to the phase diagram, and I will not have time to do the calculation, but everything is in the SciPost paper. But what I want to do before drawing the phase diagram is to make a quick introduction to RSB. So in order to compute the phase diagram, in the negative case, we will need to break the replica symmetry. This is something that you did a little bit already, but I just want to sketch how it works. So the replica symmetric matrix QAB had this form: 1 on the diagonal and Q on the off diagonal. Now, how can we break the replica symmetry? The problem is that we want to find. We have always this problem of the analytic continuation. So we need. I mean, in principle, what we should do is fix n equals 7, find the matrix QAB, fix n equals 6, find the matrix QAB, and then analytically continue the result. This is impossible. So or at least it's very hard. So what we need to do is to guess some structure of QAB that is easy to continue analytically to any n. Now, one guess, which works well, is this. So you divide the replica. I will explain. I will try to motivate it a little bit, but not so much. So your Q matrix is n by n. So what you are going to do is that you are going to break the, divide the replicas in groups of m. So you will take m times m sub-blocks of the matrix, and then and then what do you do? On the diagonal, you always have 1. Let's call it this m1. So on the diagonal, you have always 1. Here you put some q1 everywhere in the diagonal blocks. And then outside you just put q0. Why should you do that? I don't know, but I will try. I mean, this was a guess at the beginning, but then this structure has a lot of advantages. So the first thing is that these matrices like this one, they form a closed algebra. So if you multiply two matrices like that, you still get a matrix like that. If you so this means that when you do manipulations to compute the free energy, it will be easy to handle. This is not sufficient to motivate it. But the other good thing is that you can analytically continue to any n. And this is easy to see. One thing you can do, for example, is to compute the log that q term, which is quite easy, and I can give you references. And you can see that the result is, I mean, this is just a function of n, m1, q0, and q1. And you can do an analytic continuation. And OK, it's deeper than that, but I really don't have time to enter into too many details. So the only thing I'm going to say, to try to convince you that this is a good idea, is that you can compute something that I hope Federico will discuss. You can compute a very important quantity in spin glasses that is called the probability of Q, or I mean, P of Q, which is the following thing. You take two replicas with the same disorder. You take the Hamiltonian of the two replicas, and you sample x1 and x2 independently from the Hamiltonian with the same disorder, and you look to the overlap. So if you want, this is the average of x1 dot x2. Then, if you want, you take the thermal average independently for each replica, and then you do the average over the disorder, but the two replicas have the same disorder. Sorry, this is the... Try it again. OK, let me not write it. It's really, you take two x1, x2 with Gibbs distribution, you take the overlap, you make an histogram of the overlap, and you average this over the disorder. And now what you can see, and again I can give you a reference if you're interested to the calculation, it's not very hard. You can find it in the review of Castellani and Cavagna, which is called Spin Glass Theory for Pedestrians, that you already know, I think. What you can see is that, OK, in the replica symmetric, if you assume that basically you can express this object in terms of the matrix Q. So if you assume replica symmetry, you just get, let's call this Q0, sorry. You get just a delta function, OK? So if you assume that the matrix Q is replica symmetric, then it means that your distribution of Q is just going, in the thermodynamic limit, is becoming a delta function. So they always are at the same distance. While if you take this form, what you're going to get for P of Q is m1 times delta of Q minus Q0 plus 1 minus m1 times delta of Q minus Q1. So this form, this is called one-step replica symmetry breaking, tells you that it's equivalent to say that the P of Q has with some probability m, the two replicas are at distance Q0, and with some other probability, which is 1 minus m1, sorry, with 1 minus they are at distance Q1.
What is this m where you take n to be 0?
Correct. So this is, you have to find the minimum over the matrix Q. So what you have to do, at the replica symmetric level, what we did is, OK, assume this is the good solution, put this into the free energy, and then minimize with respect to Q0. Now you're going to do the same thing. Assume this is the solution. You have now three parameters, Q0, Q1, and M1, and you have to minimize over all of them, or maximize. I mean, depends. OK, maximize, minimizes. I mean, find the stationary point. Now, one important thing is that you see, if n, I mean, m, you should have that 1 is smaller and equal than m1, which is smaller and equal than n, right? But this is for n integer and bigger than 1. When you continue analytically to n smaller than 1, this is going to be reversed. It's the only way to do a meaningful analytic continuation. Because why? Because if you suppose you are able in an ideal world to solve everything, OK? So, and then you compute as a function of n, you compute m1. So you take this matrix, you put it into A of Q, and you solve it, and you minimize everything. Now okay, this is n equal to 1, 2, 3. You can do it only for integer n. And you will get, okay, when n equal to 1, it's trivial, you just get 1. For n equal to 2, you will get something. For n equal to 3, you get something else, blah, blah, blah. And now you have to do an analytic continuation of this thing, which means you have to basically interpolate these points. The only meaningful way to interpolate this point, because m1 has to be bigger than 1 when n is bigger than 1, and it has to be 1 when n is equal to 1, it must be smaller than 1. Which tells you that this is a well-defined thing. So this is, you can really interpret it as a probability, and it's going to be the probability that the two replicas have overlap Q0, which is the external element of the matrix, while 1 minus m1 is going to be the probability that the two replicas have overlap Q1. And now you see that this structure looks good to describe a situation like this, because if you fix the disorder, which means you fix the phi, and you put two replicas, with some probability they are going to be in the same cluster, so this would give a higher overlap. And with some other probability they are going to be in different clusters, which will give you lower overlap. Now, there could be other forms that are compatible with this. So why this one? Okay.
Basically, as n tends to 0, m1 has to tend to 0 as well. And so
No, because of this. You should think in this way. You have your problem at any integer value of n. 1, 2, 3, 4, 5, 6, 27, okay? You assume the matrix is like this. And now you minimize with respect to Q0, Q1, and M1. And then you do the analytic continuation. So what you know is that, I mean, when n is equal to 1, M must also be equal to 1, because, I mean, Q is a 1 by 1 matrix. In that case, the problem is trivial, okay? You don't have replicas. If n is equal to 1, you have only one replica. So for n equal to 1, M1 should be 1. For 2, 3, 4, in general, I mean, it will be bigger than 1. If M1 is equal to 1, it means that you don't have this block, so it's replica symmetric. So if you're breaking the replica symmetry, M1 should be bigger than 1. So you'll have points like that. Now you have to make an analytic continuation. So you are going to interpolate these points. Then it must fall below 1. And then when n goes to 0, it can go anywhere. There is no reason why. Okay, sorry, now I got it. You think why this should go to 0? You think that this should. I mean, there is no reason this could. This will go to some.
There is no meaning in integers anymore, so it can be whatever between 0 and 1.
Yes, exactly. M can be whatever between 0 and 1, and this depends. I mean, in the simplest possible situation, these points could be on a linear thing, okay? Or maybe they are on a parabola. If they are linear, the value of m depends on the slope. The only thing you know is that this is 1 when n is equal to 1, and then you have to interpolate the points. So m can be anything between 0 and 1. Okay, I'm spending a bit too much time on that, so maybe now at this point I ask you to believe me. And so this will be the one RSB, and if you want more details, I'm happy to discuss privately or give you references. I mean, this is really tricky, so I understand that but I cannot spend. I mean, if I wanted to talk about more physical things, so okay, this would be one RSB, and now what you can do is just iterate this. So you are going to split one of these blocks in sub-blocks, okay? So you put here smaller blocks where you put a Q2, and they have sides M2, and you can keep going, okay? And then what you see is that when you do this, you are going to add to your P of Q more peaks. So this can describe a more complicated structure. Okay, I hope you accept this. And now I'm going to show you the phase diagram. So I mean, once you accept this structure, there are 30 years of experience in dealing with these things, so we know how to do calculations, but really this would take a lot of time. So now I'm just going to sketch the phase diagram. So as a function of alpha and sigma, So here is sigma, here is alpha. So we have this line. Here is unsat. Here is sat. Ah, no, I don't like it. So here is 2. The line is going like that. And then on this side, what's going to happen? So there will be a continuation of this line. Then here I have a transition. So for all the alpha bigger than 2 and sigma equal to 0, when I cross this line, I'm going to break the replica symmetry. So I will keep being into the unsat phase, but the correct solution is going to be full RSB. Full RSB means that I have to iterate this thing an infinite number of times, but we know how to do it. It's not so complicated. And this is a continuous transition. So this is a second order phase transition. So the breaking of the symmetry will be continuous, and this is exactly what happens, for example, in the Sherrington-Kirkpatrick model. Then there is a similar line on the other side that goes like that. But, okay, now I already made a mistake. Let's change the color, because this is, at the beginning, most of this will not be very important, so that's why I will go a bit quickly. But, okay, here there is one line where you have a transition. So here it's going to be sat and replica symmetric. Here it's sat and replica symmetric. Here is unsat and replica symmetric. Here you have a transition to a 1 RSB phase, and it's continuous. And then there is a second transition, like this one here. And finally, this line is going to break into lines. So here it's sat and full RSB. I'm making a mistake. Sorry, I have to find the. Okay, let me draw it because it's a bit complicated. Here it's going to be sat and 1 RSB. And here, let's come back on that. Okay, so yes, let's do it again. So the blue lines are continuous phase transitions, so second order phase transition to a full RSB phase. So in particular, what you see is that the sat unsat transition now is always falling into a full RSB phase for any sigma negative. Then this red line is a continuous transition to a 1 RSB phase. And these green lines are the ones that you know, because they have been introduced by many people. So these are discontinuous transitions. So there is a dynamical transition of the kind of the one that Giulio introduced and Dave. I mean, this is basically an MCT transition, mode coupling transition. And this will be a Kautzmann transition. So, okay, let's discuss it once again. If sigma, let's look at constant sigma and increase alpha. So if sigma is positive, okay, it's always replica symmetric, and I go from sat to unsat, like there, and it's fine. Let me discuss first what happens if sigma is very negative, so on this line. Here I can do the drawing that is on the web page of the school. So it's the drawing that comes from a paper of Lenka, Florent, Guillaume, Federico, and Andrea. So if I am at small alpha, what I have basically a connected space where I have solutions. Okay, so the solutions form a connected space like here. So I am SAT and I am replica symmetric. When let's extend these lines a little bit. When I'm sorry, my drawings are really not good, but okay. When I reach this dynamical transition, then here it happens what Giulio described, that this cluster will break into many clusters of solutions. And also Chris, I think, described it, and maybe other people, and maybe Federico will describe it. So here you have an exponential number of clusters of solutions, and each cluster contains a finite volume of your space. When you reach this Kautzmann point, you are dominated by just a few clusters, let's say one cluster, or two, or let's say two. Okay? Then there is this blue line. What is this blue line? Is that now these two clusters are again splitting into many small clusters. So this is what is called the Garnet transition. So now your two clusters are going to become many little clusters, and then finally you become unsat, because all the clusters disappear. Now the point is, the transition from here to here is a discontinuous transition. So Q will be something here. Sorry, so here you will have just a unique Q0 because you are replica symmetric. And here you will jump to a situation where you are 1 RSB and you have Q0 and Q1, and they are different. But the transition is discontinuous, so the difference Q0 minus Q1 is going to jump from 0 to something finite. Here, nothing happens to Q0 and Q1, but the complexity, here you have an exponential number of states, and the complexity will go to 0 at the Kautzmann transition, as we have discussed many times in the school. And here the complexity is still 0, but your clusters will split into many subclusters, and this will be a continuous transition, and then you become unsat. Okay? Now, I don't want to enter too much into the details of all this, because I already spent a lot of time, but if you have questions, I'm happy to answer.
What does it mean that the replica of the symmetry is breaking and that they overlap? What are the replicas?
What are the replicas?
Why can they overlap, and does it mean anything?
So the replicas, okay, you can think in two ways. One thing is that you can think that the replicas are just a computational tool that I introduce to compute the logarithm of Z. But actually, the replicas can also be used to compute P of Q. So what you can think is that you can take two replicas, or n, but 2 is enough, and you can sample them with the same Hamiltonian, with the same disorder, and you can look to the histogram of their possible Q. Okay?
Take the system and make a copy and disorder it differently? Or take
No, same disorder, 2 copies, and you can look to the histogram of the distances of your 2 copies. And if you are in a situation like where you have clusters, with some probability the 2 copies are in the same cluster, with some other probability the 2 copies are in different clusters, and so you can get, for example, 2 delta functions in the simplest case, where you just have clusters that are different. But if you can get a more complicated thing if you have clusters within clusters within clusters, and this is what is described by the full RSB. But anyway, so the replicas are just a way to probe the structure of the energy landscape, if you want. Okay.
So the 2 copies I get are different, but the disorder is the same?
Same disorder, same landscape, and 2 probes in the same landscape. Then I make an histogram of the distances, and I average over the disorder at the end. And this is what I call P of Q. And is related to this matrix QAB. Okay?
So is the region above the first green line also 1 RSB?
This one.
No, the one.
This one.
Yeah.
Yes. This. Okay. This is what there is. Okay. This is what was discussed by Giulio. When you break this big cluster into an exponential number of small clusters, yes, this is 1 RSB, but actually you don't have a thermodynamic transition here. It's only in the, you will see it only in the dynamics. And if you do the thermodynamics, what you're going to see is that formally, if you want, you have a 1 RSB structure where Q0 and Q1 are different, but M is equal to 1. If M is equal to 1, what does it mean? That this peak is not there. What does it mean? It means that you have an exponential number of clusters, so the probability that the two replica go into the same cluster is exponentially small, so the probability that you observe Q1 is 0. So it's a kind of hybrid situation where dynamically you are going to see it, because if you start in a cluster, you stay in that cluster. But if you throw two replicas at random, they are typically going to different clusters. So that's what I don't know. It was we usually call it a dynamical 1 RSB phase. It's a jargon, but that's a jargon we use. Okay. Now, so I discussed the two extreme cases, sigma positive and sigma very negative. Now, the intermediate case is somehow not interesting for glasses. I mean, this is really specific to the perceptron. I don't want to spend too much time. What basically you see is that at some point, the alpha D and alpha K are going to merge, and the transition becomes continuous. And then at some point, this continuous transition is going to merge with the Garner, and you have just one single transition, like in this case. But OK, this is really not, it's just a curiosity of this model.
For a very small sigma, you could say that the sphere is almost flat. So can we
No, sigma is not the radius of the sphere. The sphere.
But if sigma is just very tiny along the sphere, then locally it's flat.
No, wait. Sigma equal to 0 corresponds to the fact that one constraint is excluding half of the sphere.
If sigma is very small.
Very negative.
Yeah.
Yes, it means that this is very small.
Yeah.
Yes.
Could you then interpret it as being almost flat there? That's
yes.
And thus that we are just in a simple.
It's almost a billiard in a flat space.
Right.
Yes. Yes. Thank you. This is. I mean, that's the next step. Am I done with that? Where are my notes? Okay. Okay. So I think I am done with the. For the moment, I'm done with the perceptron. And now the plan is to start talking about spheres, which is perfectly introduced by this comment. I'm lost in the blackboards. OK, I don't have it. OK, let's clean it. OK, so now, OK, the last thing I should say about the perceptron, but I will come back to this, I hope, is that, OK, this sat-unsat transition, which falls into the full RSB phase, has all the properties of jamming. It has exactly the same critical exponents. It is isostatic and all of that. But now I want to come back on this after I will have talked a little bit about spheres, because that was my other subject. Yes. Yes, the problem is that basically when at sigma equal to 0, it is isostatic. But if you want to look to the other critical exponents, the window where you see it is going to 0. So it's a bit degenerate. At any point on the left is fine. Any negative sigma. The more sigma is negative, and the better you will see the criticality.
So Z and alpha remains 1.
It's always 1. Z times alpha is always 1 for any negative sigma. Along the critical line, of course, yes. No, the sat-unsat. You cannot define if you are in the sat phase, all the constraints are positive in general. The probability that you find a constraint that is touching is 0. It's only when you reach the sat-unsat line that you really have a finite fraction of constraints that become touching. Like in spheres, if you imagine you compress spheres, if you are not at infinite pressure, in general, they don't touch. At some point, they all touch. And you jump from z equal to 0 to a finite. But I will come back. OK, so what's the plan for the following? Now, what I would like to do is today introduce the sphere problem and discuss a little bit the similarities and differences from the perceptron. And then next time, I would like to discuss the behavior of spheres in infinite dimensions, and also discuss a little bit the relation with the problem of packings. So that's B. Now, so B1, okay. How can I want to show you that, I think it should be already clear, but I want to show you that the problem of spheres can be taught really as a constraint satisfaction problem. So I want to do the same steps that I did for the perceptron, so which are here. What am I going to do? Okay, my degrees of freedom now, in the perceptron I have n real variables. In the sphere problem I have n vectors. And each of these vector belongs to a d-dimensional space. These are the positions of the particles. This is what I will call big X. Okay, and each sphere is a point in the dimensions. And now I can make two choices. Either I say, okay, I can say that xi belongs to some volume v in the dimensions. For example, I take a cubic volume, and my spheres are in this volume. Or, which connects with the comment, I can say that xi belongs to a d+1 dimensional sphere with the constraint that that xi belongs to a d+1 dimensional sphere of radius r. So I can say I have a sphere of radius r in d+1 dimension, so the surface is d-dimensional, and I can put my points on this sphere. And then I will send r to infinity, and the sphere will become locally flat. And this is, if you want, it's just it's a simple way to put periodic boundary conditions. I mean, if you take a volume, you can take a cubic volume and put periodic boundary conditions. The disadvantage of a volume is that you are breaking rotational invariance. Okay, if you are in a cubic volume, you are breaking the rotational invariance of the space, and you only recover it in the limit where the volume goes to infinity. If you do this, it's morally equivalent, but it has the advantage that now you have a sphere. Your particles are points on the sphere. They interact with some potential. And when the sphere goes to infinity, if you keep the radius of the particles fixed, it will be locally flat, and you will just get an infinite system. But now the system is rotational invariant in all the directions of the sphere. So if you want, basically the translations in the Euclidean space are rotations, and the rotations are also rotations. So you can, okay. Anyway, this is a detail. So if you are more at ease with the cubic, keep that. And then, okay. So these are my degrees of freedom, and now I have to put constraints. And what are the constraints? Just I have my index mu, that here it goes from 1 to n. I can just write it as a pair of indices ij. So mu will go from 1 to n times n minus 1 over 2. And the function h mu of x, which in the perceptron was r minus sigma, I will replace it by absolute value of xi minus xj minus sigma. Okay, so this is, so I have my variables. I have d times n variables, and I have n times n minus 1 over 2 constraints, and each of them is that variable I and variable j should be, so if this is xi and this is xj, they should be a distance bigger than sigma. But you see, it's really similar to the perceptron, except that the constraints now are not linear in X. Okay, and now I can do exactly the same thing that I did for the perceptron. So I can say, okay, let's write a partition function. I will write a Hamiltonian H, which is going to be sum over mu. So sum over mu is the same as sum over ij of some potential V of H mu, which is the usual thing. So I'm really doing nothing, but I wanted to highlight the analogy between the two problems. So the Hamiltonian will be the sum over ij of some potential v of xi minus xj minus sigma, and the partition function is going to be the integral over dx of e to the minus beta h, which is the usual partition function of a system of particles. And the potential v, again, can be any potential, provided it's negative when the argument is it's positive when the argument is negative, and it is 0 when the argument is positive. Which means that if I satisfy, I have my packing problem that I have to put spheres at distance bigger than sigma. If I satisfy all my constraints, then the Hamiltonian is going to be 0. And if there is at least one pair of particles that are on top of each other, the Hamiltonian will be positive. So the perceptron, you can think really it's the negative sigma perceptron is one particle in a sea of frozen obstacles, and the spheres is just n particles in the dimensions that interact with each other, but formally the problems are very similar. You have to satisfy some constraints. There are two important, okay. Last thing is that here I want to take the thermodynamic limit. And so what I have to do is that I will have to send n to infinity and the volume v to infinity, and I will keep constant the packing fraction, which is the density n over v times the volume of a sphere of diameter sigma, so of radius sigma over 2. Okay, can you see? I'm sorry. Anyway, I mean, it's the usual thermodynamic limit. I send n and v to infinity, and I keep the packing fraction constant. So so this is one difference with respect to the perceptron, is that I have only one control parameter, which is the packing fraction, because I cannot. I mean, basically, the volume and sigma are not independent. If I change sigma, it's the same as changing the volume. So in the perceptron, you have two control parameters that are alpha and sigma. Here you have only the packing fraction. This is one trivial difference. There are two more important differences. The first thing is that now you don't have disorder. Okay, in the perceptron you have quenched disorder, which so you have differences. Okay, this is for this is B1, 2, B1B. You have two important differences. One is disorder, and the second is the crystal. So in the perceptron you have a disorder, so the obstacles or the inputs, I mean the phi, are disordered and they are quenched. Here you don't have any quenched disorder. You just have a sphere and particles, and you have constraints, but the constraints do not contain any disorder. And the second thing is that because you don't have disorder, you also have a crystal. So you know that, okay, this has been discussed by Henry Cohn in 2 and 3 dimensions. For example, if you want to maximize the density, and at the same time you want to satisfy the constraints, you are going to get a crystal. So the first thing I would like to say, which at this point should be quite clear, I hope, is that so if you keep the crystal, I mean, if you don't do anything and you just say, okay, I have this constraint satisfaction problem, I have to satisfy the constraint that the spheres should not overlap in the dimensions, and you increase the density, what you're going to see is that your SAT-unsat transition is exactly the close packing of the crystal. Okay. So if you take, for example, the pressure versus the packing fraction, you're going to have some liquid phase. Then you're going to have some transition to the crystal, and then the pressure is going to diverge at the close packing point. So this will be liquid, this will be crystal. And this, if you want, is the behavior in the SAT phase. So the SAT phase is when you satisfy all the constraints. So the particles are not overlapping, and in the SAT phase, if you remember the partition function, when temperature goes to 0, the partition function is uniform over all the solutions, which means that you are giving the same probability to all the possible configuration of hard spheres at the same density, at the given density, which is the equilibrium state of hard spheres. Okay, so the equilibrium state of hard spheres will have a liquid state, then a first order transition, then a crystal, and the pressure, actually not the pressure, but the pressure divided by temperature, right? Because okay, I'll come back to that. The pressure is going to diverge at the close packing. So this is really this is the SAT and SAT transition for the sphere problem. Okay, if you don't remove it, and if you want, you can plot the pressure, but you can also plot the entropy. So if you take the entropy of hard spheres as a function of packing fraction, what do you get? Now let me try to not make a mistake. So you get the liquid entropy like this. You get the crystal entropy like this. You get the phase coexistence here between liquid and crystal. Perhaps it's not going, it's always decreasing with, it's hard to draw, but okay, you see. Okay, so you get the liquid, you get the crystal, and at the close packing point, the entropy of the crystal is going to minus infinity, right? Exactly as it was doing for the perceptron when I approached the SAT and SAT transition from the SAT phase. The entropy is going to minus infinity because the space of solutions is going to 0. It's going to a point, which is the close packed crystal. Okay, that's fine. And similarly, if you look to the energy, you know that our hard spheres have 0 energy. And when you reach close packing, and if you keep compressing your crystal, you will create overlaps, the particle will start to repel, and you will have an energy, which is going to go like phi minus phi close packing square, as in the perceptron. So everything goes like in the perceptron, in the crystal, right? So if you want the crystal, you can think to the crystal really as the perceptron for positive sigma. So the crystal is a single pure state. Yes?
I've lost track of what's happening with the dimensionality of the problem.
For the moment it's variable, but I was thinking to 3 dimensions, for example. Let's take 3 dimensions. This drawing is for 3 dimensions. So what I wanted to say is that you can really think that the crystal is behaving like the perceptron for positive sigma. So the crystal is a single minimum of the energy. If you plot your Hamiltonian versus the coordinates, when you are in the crystal phase below close packing, it's going to look like that. So this is the crystal at phi smaller than the close packing. So there will be a bunch of configurations because you can move your spheres a little bit without overlap. And when you reach the close packing and you go above it, your crystal will be a well-defined unique minimum with positive energy of the free energy of the energy. So you can call the close packing point of a crystal a SAT and SAT transition or a jamming transition, but it behaves like this one. It's just a single state, and it's also not like the perceptron for positive sigma. It is not critical. It is not critical because at this point the system is hyperstatic. For example, in 3 dimensions you have 12 neighbors in the FCC structure, so it's not going to be. It's a SAT and SAT transition, and it's not critical like the one of the perceptron at positive sigma. So we would like to study the jamming transition of amorphous states, not of the crystal. So what are we going to do? I lose my notes. Okay, what we are going to do, there are 2 possible ways that have been studied in the literature, and then I will stop. So the first one is to introduce some disorder. And of course, you can think to introduce some polydispersity. So the first solution is to introduce back some disorder in the problem. This can be polydispersity. So this has been discussed by many lecturers before, by Ludovic, by Gilles, and so on. So if you introduce polydispersity, maybe there is still a crystal, but you're not going to see it, so you can forget about it. And there is also another way that has been proposed by Kreiknan in '62 in the context of liquids, but more recently by Marie Florent and Kursan, which is to add some disorder into the constraint. So replace. So polydispersity would be to replace h mu by hi minus xi minus xj minus sigma ij. So you put disorder in the sigma, in the diameters. This Mari MK, we call it sometimes MK model or MKK model, depends on the versions, but this would correspond to add a disorder here into the distance, so randomly shifting the particles. And it has the advantage that the system remains somehow monodispersed. You have a single sigma, but okay, it's not very physical because you are randomly shifting the particles. But it has, it has a lot of advantages. Anyway, you can choose one of the two. And the second solution, that is one I want to discuss tomorrow, on Thursday, will be to increase dimension. And basically what you can see is that for d bigger or equal than 4, it becomes very hard to crystallize. And in 4 you can sometimes crystallize, but in 5, 6, 7 it becomes really impossible to crystallize. And this is really connected to what Enrico said. Because if it were easy to crystallize in large D, but we just simulate the system, it would crystallize, and we would know the densest crystals in large D, which is not the case. So it's really, when you increase D, you are going to stay in the liquid. You will never nucleate the crystal, and the liquid, something will happen anyway, but the entropy of the liquid at some point, let's say of the glass, because it will become a glass, when the entropy of the glass will go to minus infinity, this will define the amorphous version of the closed packing point, and this will be the interesting one for us. So that's what I'm going to discuss next time. And I think that's it.